So it started.
Yeah, it is live. So, shall we start?
Yeah.
Yeah, okay. Good afternoon, everyone, and welcome to the online lecture series on atmospheric dynamics and its applications to climate sciences, which is jointly organized by South Asian Meteorological Association, SAMA, and Savitribai Phule Pune University, SPPU. So today we have in this series lecture number 6, which will be given by Professor Dr. Anandakumar Karipot. And before he delivers his lecture, I would request that the welcome address be delivered by Dr. Madan Lal Shrestha sir, who is Vice President to SAMA and also an academician, NAST, and former DG, DHM, Nepal. Sir, please, your welcome address.
Yeah, thank you. Thank you, Rohinji. I think, first of all, I think I must thank Pune, Savitribai Phule Pune University for making all these arrangements. And I think it gives me a pleasure to welcome all the participants and the colleagues. I think these are some of the occasions, I think, when we meet and interact with each other. And as a vice president of SAMA, it gives me a pride to see such kind of activities going on. And it's a weekly series. And, whenever we talk about the lecture, it takes me back to my university days, as Tyagi Sahab has mentioned, my under-university days, more than a half century back. So still it gives me pleasure to remember all those days. So I think today's lecture is on the natural coordinate systems, cyclonic and anti-cyclonic gradient flow. And it's very basic and very necessary for the meteorologists to learn. And it is delivered by distinguished Professor Anandakumar Karipot from SPPU Pune. I think I would like to welcome Professor Saab. I think it's our pleasure, and maybe I think the participants, we have, I think, more than 125. I think they will really be benefited with your, lectures. And at the same time, I think I would like to urge all our participants, to involve very actively and get most of the content from this lecture series. So I think I don't want to take much time. And again, I welcome you all, especially our candidates, the participants, I think, who will learn a lot. I think I'm sure of this. And I wish all the best to our participants. And at the end, again, I would like to welcome Professor Karipot for the lecture. Thank you very much.
Thank you, sir. Now, it's my pleasure to introduce Professor Anandakumar Karipot. So I would be just sharing my screen. So Professor Dr. Anandakumar Karipot, he is presently as a visiting professor in Savitribai Phule Pune University. He superannuated as professor in May 2024 from the Department of Atmospheric and Space Sciences, SPPU. And prior to joining our department, that is Department of Atmospheric and Space Sciences, which was in October 2009, he worked as a postdoctoral researcher in National Aerospace Laboratories, Bangalore from 1997 to 1999, after which he has also worked as a research scientist in University of Georgia, USA for a long time. He is a very favorite teacher of all the students since 2009. So he has taught different subjects, which is atmospheric science for MSc and MTech students, in which the courses are dynamic meteorology, boundary layer meteorology, atmospheric instrumentation and observation techniques. Of course, all the labs which he is taking, Fortran, and as well as the numerical methods and NWP labs. His research topics are related to understanding atmospheric processes which are close to the Earth's surface, atmospheric boundary layer, and micrometeorological measurements. He is basically MSc from Cochin University of Science and Technology in Physics, MTech in Atmospheric Sciences from again QSAT, and PhD from University of Bonn Kultur, Vienna, Austria. He has nearly published more than 50 papers in peer-reviewed journals, while he has supervised around 4 PhD students, and 2 of the students are ongoing. So I'm really happy to welcome you, sir, and I request you to please deliver the lecture.
Okay, thank you, Dr. Rohini and Dr. Shrestha, and Sama for giving me this opportunity to deliver this lecture. Let me share my slide. Okay, so good afternoon to all, and maybe good morning to those who are attending from the far west. So today's lecture is basically on the natural coordinate system, and with the help of the equations in natural coordinate system. So we'll be looking at the different types of balanced flows as well. So talking about the natural coordinate system, so in the past few lectures, we have gone through the momentum equations, basically in Cartesian coordinates, and the equations were presented in the vectorial form, and I think the spherical coordinates were also discussed. And with the help of that, we could explain some of the physics involved. And but when it comes to discussing the rotating motion, and especially the different forces involved, it is more convenient to express the equations in this natural coordinate system. So initially I will be going through some of the basics of this natural coordinate system. So one of the most important aspect is that this coordinate system is not stationary. The coordinate system moves with the flow. So that is one of the most important aspect of the natural coordinate system. So as you can see in this figure here, so it moves with the flow, and then we have to fix the axis. So one axis is always tangent to the flow, what is marked as with the help of the unit vector t. So that we have to fix tangential to the horizontal wind at each and every instant and each and every location. And then we have to fix the next axis, the n axis, we fix it as normal to this tangential vector t. So that we have to keep in mind. So t is always tangential to the flow, and n is normal to it and directed to the left. So these two things we have to keep in mind. And then the corresponding unit vectors we can represent using t, n, and k, k being in the vertical. And the coordinate locations we represent as s, n, and z. If it is in the Cartesian coordinate system, we represent using x, y, and z. But here we use s, n, and z to represent the locations. So now, another thing we have to remember is that, so our main interest is to discuss the forces and their balance involved in curved flow. So the radius of curvature. So we have to we have to also follow the convention when we talk about the radius of curvature. So once we fix the t and n, so then r is taken as positive if it is to the left of the flow. The curvature, if it is to the left of the flow, that is in the same direction as that of n. So then we can, so this way r is positive, and if the curvature is in the other way, that is in the clockwise direction, then r is negative, and that means it will be in the opposite direction to the unit vector n. So these aspects we have to remember to follow what I'm going to discuss in the coming slides. So, so here for the wind vector, we don't have the U and V components here. So because it is always along that tangential vector. So the vector V, we represent it as V multiplied by the unit vector T. And whereas the speed we can write as ds by the total derivative of the displacement s with respect to time. Then the acceleration. So what we are going to do is we need to get this equation for the equation momentum conservation in natural coordinates, basically in the horizontal. So so first we have to look at what is how to represent the acceleration. So the acceleration, so we can represent in this particular form d by dt, the total derivative of the wind vector v, and wind vector v we are writing as v t, so d by dt of vt, and applying the chain rule we can represent that as t dv by dt plus v dt by dt. So the total derivative of this unit vector t we can express in a more convenient form as following these steps what I'm showing in this slide. So we can think about this rotating motion. So initially, let's say the air parcel is at this particular point, and after an infinitesimal time, it has followed this curved path and it has reached here. So that means it has traveled a certain distance, delta s, and the angle involved is delta phi. So from this geometry, then the angle delta chi we can write as delta s by r. R is the radius or curvature. And from this, so, and we can also consider this geometry. So from that, we can write delta chi as delta t by t. And this is the magnitude of t unit vector. So we can write it as just delta t. So that way, delta t we can write as delta s by r. So now dividing that throughout by delta s, so we get delta t by delta s equals 1 by the magnitude of r. And if you take the limit delta s tends to 0, then we can write it as a total derivative dt by ds equals unit vector n by r. So we can see that the direction of this change in the unit vector t is parallel to that of unit vector n. So that way we can write now. So we wanted to replace or express dt by dt in another form. So dt by dt initially we can write as dt by ds multiplied by ds by dt. So now we substitute for dt by ds from here. So then we can write the total derivative of this unit vector t with the time. We can write it as v multiplied by n by r. So then the acceleration, that way it becomes dv by dt equals t dv by dt plus v square by r n. So we are writing it in the component form. One is along that tangential axis, and then the other component is perpendicular the tangential actor, that is in the direction of unit vector n. So now, so this is the acceleration. So this acceleration, according to the momentum conservation, so this acceleration should be equal to the sum of all the forces acting. So now we can look at how can we express the forces involved. So basically we have all different forces: the pressure gradient force, the Coriolis force, centrifugal force, gravitational force, and the frictional force. But here our interest is in the horizontal, so we don't consider the gravitational force, and we are neglecting the frictional force. So we will be looking at only the other three forces: the pressure gradient force, Coriolis force, and the centrifugal force. So pressure gradient force, so here instead of using height as the vertical coordinate, we use the pressure as the vertical coordinate. So in that case, we will be using the pressure gradient as equal to the gradient of the geopotential along on a constant pressure surface. So that way, we can express the pressure gradient del phi equals at the constant pressure surface equals minus dou phi by dou s along t minus dou phi by dou n along the unit vector n. So the terms on the right hand side, the first term on the right hand side shows how the geopotential, phi is the geopotential. So how that is changing along the direction of the flow, along the direction of the motion. And the second term shows how phi is changing, the geopotential is changing perpendicular to the direction of the flow. So now the Coriolis force we can write as minus f k cross v. And here, so if you take the cross product, then the two, in this case, there is only Coriolis force acts perpendicular to the flow. So we will not be having any T component for the Coriolis force. So for the Coriolis force, that way we'll be having only one component which we can write as minus Fv n. And then anyway, the centrifugal force already there as part of that acceleration we have derived. So the momentum equation that way we can express it as the acceleration which is given by these two terms, dv by dt plus v square by r along the t axis as well as the n axis. So that is the acceleration. So that equals the pressure gradient force plus the Coriolis force. So now both sides we have the T and N component. So we can separate out this T and N component. T component, we can also refer it as the S component. So that is, so dV by dt, so that is equal to minus dou phi by dou s. And the N component we can write as v square by r from here, and Fv is here. So plus Fv equals minus dou phi by dou n. So basically, now we have got two equations in this natural coordinates. The first equation, which is marked as E7 here. So that is the change in the horizontal velocity with the time along the direction of the flow due to that change in geopotential along the direction of the flow. And the second equation basically represents the balance among all the forces involved. So the first term here represents the centrifugal force. Second term represents the Coriolis force. And the third term represents the pressure gradient force. So now we can look at some special cases. So if the flow is parallel to the geopotential height contour. So for example, as shown here, so we have the geopotential height contours marked as 5 and 5 plus delta phi. But if the flow is parallel to these geopotential height contours, that means there is no gradient in this particular direction of the flow. In this particular direction, there is no gradient in the gradient is across the flow. So in the direction of the flow, there is no gradient in geopotential. That means dou phi by dou s becomes 0. So from our first equation, that S component equation becomes the total derivative of V equals 0. So that means V, the wind speed, will be constant. So that is a special case what we are getting from that first equation. So that means that it's a steady state flow, no change in the speed. And then we can make use of the second equation. So from the first equation, we get that no acceleration, the speed is constant. And then we can make use of the second equation, which is the N component equation, given by the sum of, which gives the sum of the three terms, three forces involved, the centrifugal force, Coriolis force, and the pressure gradient force. So using this n component equation, so now we can think about different types of flow. So three forces are there in this particular equation. So we can think about different combinations, the balance among any two of these forces, or also we can also think about the balance among all the three forces involved also. So now we move on to the balanced flows. The different types of balanced flows involved are geostrophic flow, inertial flow, cyclostrophic flow, and the gradient flow. So basically, these are kind of idealized flows created by the balance of different horizontal forces. Basically, the three forces which are involved in the in this equation. So we should remember that. So what we are looking at basically will be a qualitative way only to understand the different types of flows and the force balance involved in those type of flows. So we, while describing these balance flows, so we assume that assume steady state condition. That means the V is constant in this case. And of course, we use the natural coordinate system. And also, we are not going to look at the vertical velocity component also. So we strictly stick to the horizontal flow. And a few more things we should remember, that some of the basics which I think already discussed in the previous lecture. So Coriolis force basically deflects the flow to the right of its motion in the northern hemisphere. And centrifugal force always acts radially outwards. And the pressure gradient force, it acts from high pressure to lower pressure. But if we are expressing the force with the height as the vertical coordinate, but if it is isobaric coordinate with the then we will be expressing the pressure gradient force in terms of the geopotential gradient on a constant pressure surface. So there also the force acts from region of higher geopotential height to lower geopotential height. And an associated feature is that if we have a low at the surface, the geopotential height of constant pressure surfaces aloft will be lower compared to the surroundings, which we usually call it as a trough. And the opposite behavior vice versa for if there is a surface high. So please keep these few things in mind to understand the balanced flows we are going to discuss. So now first we take up the geostrophic flow using this natural coordinate system. So basically the n component equation, because we assume that the flow is parallel to the geopotential contours. So geostrophic flow, basically it is a balance between the Coriolis force and the pressure gradient force. But if you look at the n component equation, so we have all the three forces. So here we will have to find a reason to neglect this centrifugal force. So that means for this balance to occur, so this V square by R term should vanish. So that can happen if R is very large. That means if R tends to, the radius of curvature tends to infinity, then it is almost like a straight line. So then we can neglect this term V square by R. And then we can write this n component equation. Then we are left with the Coriolis force and the pressure gradient force. So we can write and we can replace V with Vg, because that's what we are talking about now is the geostrophic wind resulting from this balance. So we can express the n component equation in this form: FVg equals minus dou phi by dou n. And the geostrophic wind we can write as minus 1 by F dou phi by dOA. So that is what is represented in this particular figure here. So we have this geopotential gradient perpendicular to the direction of the motion, and the Coriolis force always acts to the right, so it is shown in this way, and the pressure gradient force is acting exactly opposite to that, and so there is a balance between these two, and so that balance we call it as the geostrophic balance, and the flow resulting from that is the geostrophic wind. And one more thing to remember is that for this balance to occur exactly, so we will have to neglect the influence on F. That means the Coriolis parameter. So for that, the height contours will have to be parallel to the latitude circles as well, because if the latitudes are changing, F is changing, so we'll have to look at that as well. And the second type of flow is called the inertial flow. And so this is a kind of really very special case which usually doesn't exist in the atmosphere at all, because we are talking about the balance between the Coriolis force and the centrifugal force. And we know that almost always for a flow to exist, there has to be pressure gradient force, and if that is negligible, then the flow will not sustain very long. So it is assumed here that the pressure gradient force is negligible or very, very small or balanced. Whatever is there, it is balanced by the frictional effects. So with that assumption, we can talk about the balance between the Coriolis force and the centrifugal force. So it is almost like the flow is happening without any other external forces. The forces present are Coriolis and centrifugal force, which we are introducing to explain which are fixitious forces, we call it, to explain what we are observing. So and here we are talking about only those two fixitious forces. So if we neglect the pressure gradient force, then the n component equation becomes v square by r, which represents the centrifugal force, and Fv, which represents the Coriolis force. So v square by r plus Fv equals 0. So that this equation basically represents the inertial flow. And from that equation, we can solve for the radius of curvature as r equals minus v by f. And then with the assumption of that flow parallel to the geopotential height contours, so speed is constant. So v is constant. So that means the radius of curvature, and assuming that the f is, or neglecting the latitudinal dependence of f, or if you consider that the change in the latitude is not very large, so then we can say that the r is also constant, because v is constant and we are neglecting the influence of f, and so r is that way we can take it as constant. So, and then you see that r is negative, minus v by f. So r is negative means then the flow has to be it has to be clockwise, anti-cyclonic case, because r is negative. And we can look at the periodicity involved with this anti-cyclonic motion. So which we can, so 2 pi is the circumference, 2 pi r by v. We can write the period as 2 pi r by v, and then r is minus v by f, which we can substitute there, and then which we can write as 2 by f. F is 2 omega sine phi, and 2 pi by omega is the angular velocity of rotation of the Earth. So 2 pi omega is basically one full day. So here it is 2 pi by 2 omega. So it is a half day by sine phi. So which is the periodicity associated with the inertial flow. And so we can also express this as the inertial flow period is as equal to 1/2 pendulum day. So I mentioned already that though theoretically we can talk about this type of balance, in the actual atmosphere doesn't usually exist because for the flow to sustain, we need to have pressure gradient force, but we are assuming that the pressure gradient force is either doesn't exist or very, very small, but it can exist over the ocean currents. Some of it we can explain with the help of this type of force balance because the at the ocean surface, the transient winds can act as the driving force, and then we can talk about this type of balance, but really doesn't exist in the atmosphere. Okay, now we move on to the third balance flow, which is called the cyclostrophic flow. So here again, it's a balance between two of the three forces involved in that n component equation. So here we say that this is the balance between the centrifugal force and the pressure gradient force. So that means the centrifugal force has to be large compared to the Coriolis force, because we will be neglecting the Coriolis force. So that means the centrifugal force has to be much large than the Coriolis force. So naturally, so Coriolis force we usually express as Fv, and centrifugal force is V square by R. So if V is large, then the centrifugal force will be much larger. So because it is expressed as V square by R. And in that case, and if R is also small, for small scale systems like tornadoes, typically of the diameter 100-200 meters in radius, and the wind speeds associated with such systems are also very, very large, 50 to 60 meters per second. So it satisfies R is small, and the wind speed associated with that is also very large. So that way we can kind of neglect the Coriolis force and express the balance between the centrifugal force, which is V square by R, and the pressure gradient force, which is minus dou phi by dou n. So now we can solve this to express V as square root of minus R dou phi by dou n. So this equation basically represents the wind speed associated with this cyclostrophic flow. So if you so now we can look at, so we got this expression for V, but it is square root of minus R dou phi by dou n. So V is the speed. So the solution, whatever value we get for V, it has to be positive, since V being just the speed, and it has to be real. So we can take the values which give the values for R and dou phi by dou n, which satisfies V has to be positive and also the real. So that way there are two possibilities. So minus R dou phi by dou n has to be greater than 0 in order to have a positive and real root. So this will be satisfied for two conditions. Either it can be R can be greater than 0 and dou phi by dou n less than 0. Then we can get this minus R dou phi by dou n as greater than 0. And another possibility is that R can be less than 0, but then dou phi by dou n will have to be greater than 0. So with this condition, what type of curved flow are possible is represented here. So the way we look at is that once we say that R is greater than 0, so that means it is counterclockwise. It has to be counterclockwise motion, and then we can fix the direction of the n. So n has to be to the left of the flow direction. So this is the direction of the flow, counterclockwise, and n has to be to the left. So then we can look at, so here we say that dou phi by dou n has to be less than 0. So that means in the positive n direction, so this is the positive n direction. In the positive n direction, the geopotential should decrease. So that is possible only if the law is at the center. If it is L here and this is the positive n direction, then dou phi by dou n will be greater than 0. As n increases, geopotential height also will increase. So we cannot have a high at the center here. So in order to have a low at the center, no, in order to for dou phi by dou n to be less than 0, that means as n is increasing in the positive n direction, phi should decrease. So at the center, it should be a low. And then, of course, if the L is at the center, then the pressure gradient force will be directed towards the low. So the pressure gradient force we can mark in this direction. And the centrifugal force, anyway, it's always directed radially outwards. So that way, we can see that the force balance between the pressure gradient force and the centrifugal force corresponding to the first situation, which is R greater than 0 and dou phi by dou n less than 0. So here what we are getting is the counterclockwise motion and with the low at the center. And we can also look at the second situation, which is R less than 0. So that means the flow has to be in the clockwise direction. But again, dou phi by dou n has to be in this case greater than 0. So this is the flow direction, and n again is directed in this way to the left of the flow direction. So in this case also, for dou phi by dou n to be greater than 0, so there has to be L, the low at the center. So in this case, second case also, the system should have low at the center, but in this case, it is going to be clockwise circulation. So, but what we usually see, this is the northern hemisphere. So what the type of flow that exists in the northern hemisphere is the associated with the cyclones and also with the tornadoes. It is the counterclockwise or cyclonic motion. So here the balance we are talking about is that the balance between the pressure gradient force and the centrifugal force. So though the Coriolis force is not coming into picture explicitly when that initial, because it originated from actually the tornadoes and all originate from a large scale system, and so initially, so there will be influence of this Coriolis force, which will turn the flow to the right, and what results is the counterclockwise flow. And as a result, most of the time we observe counterclockwise cyclostrophic motion, like as in the normal tornadoes. But rarely this type of tornadoes are also seen or are reported are only 1% of the total tornadoes. This type of clockwise motion also reported, but it used to be usually not so intense tornadoes. Okay, now we move on to the fourth type of balanced flow, which is called the gradient flow, involving the balance among all the three forces. Involves the balance between the pressure gradient force, Coriolis force, and the centrifugal force. So here also we assume that the flow is parallel to the geopotential height contours. So with the help of that, we take the speed we take as constant, and then what we have is the n component equation representing the sum of the three forces. So a quick look at the main difference between the geostrophic wind, which involves the balance between pressure gradient and the Coriolis force. So basically, it is a straight line motion. There is no curvature, no acceleration. And here, in the case of gradient wind, so we are introducing the curvature. We are including the centrifugal force also. So then that way, wind speed also will be influenced as a result of that. So the flow will not be along the straight line. So the n component equation, we can multiply throughout by r and rewrite it in this particular form, v square by r plus frv plus r dou phi by dou n equals 0, which is in the form of a quadratic equation. And the solution of the quadratic equation, that way we can represent as v minus fr by 2, and then positive plus or minus, the positive as well as negative roots are there, f square r square by 4 minus r dou phi by square root of this term. So this way, so we can expect that the gradient wind is a better approximation compared to the geostrophic approximation, because all the three forces and the curvature we are including here. And here also we can look at different solutions. So here we can see that, so this is the expression we are having. And here also we should make sure that whatever values we give for r and dou phi by dou n, or the sign we associate with the r and dou phi by dou n, it should result in positive v, because it is the speed, and also it should be real. So v should be real and positive, so that the condition exists here also. And with that condition, we can look for different combinations, combinations for r and dou phi by dou n, to make, but should make sure that we should be real and positive. So we can look at the cases one by one. So initially we are taking the case r greater than 0, both r as well as dou phi by dou n greater than 0. And then there are positive root as well as negative root. So if you look at the negative, so in this case, we can see that. So r is greater than 0, so that means this term will remain as negative. And then if you take here dou phi by dou n, both are, so this term will also remain as negative. So within the square root, so so then we will be, and then after taking the square root, it will be we are subtracting this term from f square r square by 4 and then taking square root. So then you are adding to minus fr by 2. So it is going to remain as a negative value. So we will be negative here and here also, because we are subtracting this from this negative quantity. So in both cases, the v is not going to, v is going to be negative only. So it can be complex also. So this is not going to exist. We cannot be negative and we cannot be imaginary also. So it is unrealistic to have this type of a situation. But I'll just explain that how we can define this type of a flow. So what we are saying is that, again, r is greater than, we say that r is greater than 0. So that means the flow has to be counterclockwise. So initially we can fix the flow direction in this way, and then we can fix the n axis. So it has to be perpendicular and to the left. And then we are saying that dou phi by dou n, the geopotential gradient is positive. That means geopotential gradient should increase in the n direction. So that means at the center we should have a high. So once we fix that, then we can fix the direction of the forces. Since at the center we have the high, and then the pressure gradient force is directed, it has to be directed from high away from the center, so which is marked here. And then of course centrifugal force acts radially outwards, and the Coriolis force acts to the right of the motion. So in this case, so that way all the three forces, so all the three forces we can see that it is acting in the same direction. So one thing is that we don't see that v is becoming negative or imaginary. So that way we cannot have. But then again we see from this figure that all the forces are acting in the same direction. Then we cannot have a balance among the three forces. Okay, so this particular case is unrealistic. So then we can move on to the another case. We keep r as positive or greater than 0, and then dou phi by dou n less than 0. So if it is r greater than 0, then again, so we can fix the direction. I'm not going to explain this again and again. So, so in this case, so we can, so this has to be a low at the center for this to be satisfied, because dou phi by dou n is less than 0. So for that to be true, we need to have a low at the center. And once we fix that, then we can mark the direction. Pressure gradient force has to be towards the center, and centrifugal force anyway acts outwards, and Coriolis force to the right of the motion. So centrifugal force and Coriolis force will be acting away from the center, and the pressure gradient force is acting towards the center. So this type of flow is realistic. It's often observed in the atmosphere, which we know that. So this is possible. So because of that, we call it as a regular flow, which is resulting from r greater than 0 and dou phi by dou n less than 0, and that is resulting from the positive route. But if you take the negative route, the V will become negative. So here minus FR by 2 minus of this quantity, and that will result in a negative value for V, which is not possible. So that way, from this condition, from this situation, so we will take only, we can consider only the positive route. And the flow resulting from that is corresponding to the flow around a regular low. And we also call this type of flow as a baric flow because the pressure gradient force and the Coriolis force are acting in the opposite directions. And for such type of flows, we call it as the baric flow. And this is very common in the atmosphere. The balance pressure gradient force balancing the Coriolis force and the centrifugal force, and it is existing in the typical low pressure systems as well as mid-latitude cyclones. Now, moving on to another case, which is r less than 0, dou phi by dou n greater than 0. So theoretically, this is possible. So we can, corresponding to the positive route, we can get a positive value for V. But then if you look at the situation here, you can see that the pressure gradient force and the Coriolis force is acting in the same direction, and the centrifugal force alone is acting in the opposite direction. So that means the pressure gradient, the centrifugal force will have to be very large in order to balance the sum of pressure gradient force and the Coriolis force together. So such type, which is not very realistic, and this type of flows really doesn't exist in the atmosphere. And for that reason, though it is theoretically possible, it really doesn't exist in the atmosphere. For that reason, we call it as the anomalous low. And moving on to the fourth case. So here we take r less than 0 and dou phi by dou n less than 0. And from this case, we can look for two possible type of flows: the regular flow, regular high, and the anomalous high. So the situation what is arising from here, so you can, it can be either positive route or negative route. Theoretically, both will result in positive and real values, provided so within this in this radical, the square, within the square root, we have these two terms, f square r square by 4 minus r dou phi by dou n. So for this to be positive, we need to, since r is taken as less than 0 and dou phi by dou n also taken as less than 0, for this to yield a positive value, so we need to apply certain condition, f square r square by 4. That means this first term should be greater than r dou phi by dou n. Otherwise, this will yield a negative value, and then we get a imaginary root here. So to avoid that, this condition has to be satisfied. F square r square by 4 should be greater than r dou phi by dou n. So this will yield a positive value, and then we can get a positive and real solution for V from this equation. So then again, looking at r less than 0, So R less than 0, then we need to have a clockwise or anti-cyclonic circulation. We can mark that, and then dou phi by dou n. With respect to that, then n is in this direction, to the left of the flow direction. This is the flow direction, and to the left of that is the n direction. So then dou phi by dou n will have to be, to satisfy dou phi by dou n less than 0, then the high will have to be at the center. We need to have a high pressure, and then we can fix the direction of the other forces. Pressure gradient force will have to act away from the center, and Coriolis force is to the right of the flow direction. This is the flow direction, and Coriolis force has to be to the right. Centrifugal force acts away from the center. So that means it is possible to have that type of a situation, and from this condition we can say that dou phi by dou n, the absolute the magnitude of dou phi by dou n will have to be less than r f square by 4. So now theoretically, for this case, we can have positive, both positive and negative roots will yield the two possible scenarios with the condition that this condition is met. So this has to be satisfied, and then we can have the possible scenario. But here also we have both regular, what is actually possible, and what is only theoretically possible. So first we take up the anomalous case, which is corresponding to the positive root. So minus fr by 2 plus we are having this term. So here we are taking r as negative, and dou phi by dou n is also negative. So that may, and then we are subtracting this term. But since we are adding this term, r is less than r is negative, so this will yield a positive value, and then we are adding something more to it, positive value adding to that. So that means what the v will be much more than fr by 2. So positive fr by 2. So that means the value, we can think about a typical, take an example and look at it. So for this to be true, then that means the balance of forces is coming like this. Coriolis force acting towards the center alone, and pressure gradient force as well as centrifugal force is acting away from the center. And so for this balance to happen, the sum of these two, Coriolis centrifugal plus pressure gradient force, should balance the Coriolis. That means the, and here we are saying that V is going to be greater than FR by 2. That means V is quite large. So this can be true only if the pressure gradient force is very, very small. So for a very small pressure gradient force, you look at this example given here, mid-latitude locations, we can take Fs 10⁻⁻⁴ per second, and a very small pressure gradient, 1 millibar per 1 HPA per 100 kilometer, and a large system like with the radius of curvature as 1000 kilometer. So even for such a system, we see that if you solve this, we see that the value for V, we get 89, close to 90 meter per second, which is very unrealistic for a anticyclone, for a high pressure system. So it usually doesn't exist for such a very low, small pressure gradient. Having such high wind speeds, not realistic. So we call it as an anomalous high condition. And corresponding to the negative root of the equation, the solution for V. So we are subtracting this term from FR by 2. So this value will be sufficiently small. So then we can think about, in this case, the pressure gradient force can be can be even more than the centrifugal force. And then we can think about this balance for sufficiently low values of the wind speed, which is realistic. So we call it as the regular high. And some of the details, so we already discussed that this condition has to be met. So some of the special situations, like we can look at why at the center of the anticyclones, the wind speeds are very small. So from this situation, we can see that as R tends to infinity, R tends to 0, that means close to the center of the system. So this pressure gradient naturally will have to be very, very small. So the winds also have to be very light, close to the center of these anticyclones. And again, in anticyclones, Coriolis force alone has to balance the pressure gradient force and centrifugal force. So, and Coriolis force is proportional to V and centrifugal force is proportional to square of the speed. So, balance will happen for very, so in the case of cyclones, balance can happen because the pressure gradient force is balancing the other two forces, whereas in the case of anticyclones, Coriolis force alone has to balance the other two forces, so V cannot be very large. Whereas in the case of cyclones, V can be sufficiently large and still the balance can be achieved. So this is just the summary of the cases we already discussed. And usually what is observed is that normal highs tend to have low wind speeds than normal lows. We already mentioned the reason for that. And again, the summary of the four different possibilities. And remember that among these only two really, the regular low and regular high only actually exist in the atmosphere. The other two are only theoretically possible. So we call it as the anomalous cases. And we can also look at now. So the gradient wind is close to the real wind, whereas the geostrophic wind is highly approximated. So we can look at the relationship between these two types of flow, the gradient wind and the geostrophic wind. So Vg, from that geostrophic balance, we have got this relation Vg equals minus 1 by F dou phi by dou n, which we can substitute in our the gradient wind solution. Instead of minus dou phi by dou n, we can substitute as minus F Vg. And so that equation we can write in this form. And we can rewrite in this form as the ratio between, from this, we can write the ratio between the geostrophic wind and the gradient wind as 1 plus V by Fr. So, and when R is greater than 0, that is counterclockwise or cyclonic flow. So if Fr is greater than, we are trying to interpret what does this mean. So if R is greater than 0 or Fr greater than 0, then that is 1 plus some positive quantity. So that means Vg, that way, from this relation, Vg will have to be greater than V. So that means that in such situations, in cyclonic type of flow, if the curvature is counterclockwise, then it is like the geostrophic wind is overestimating the actual wind, because we consider the gradient wind as close to the actual wind. So in cyclonic flow, the geostrophic wind is overestimating the actual wind, whereas in the case of anticyclonic flow, that means in the case of high pressure systems, so then this becomes Fr is negative, so 1 minus V by Fr. So that means the geostrophic wind will be underestimating the gradient wind or the actual wind. So and in from the observations and all that and calculations, it is seen that over the mid latitude regions, the difference between the gradient wind and the geostrophic wind is relatively small, within the order 10 to 20% difference between Vg and V. But in the tropics, the geostrophic approximation is not really valid, and so gradient wind, the difference between Vg and V much large. And people often look at the edge geostrophic component of the wind by taking the difference between the gradient wind and the geostrophic wind as VA, which the vectorial in the vector form VA is gradient V minus Vg, and which we call it as the edge geostrophic wind. So with this, I am closing this lecture, and basically I refer this textbook, Introduction to Dynamic Meteorology by J.R. Holton, and you can also refer other books such as Dynamical and Physical Meteorology by Holtner and Martin. So once again, thank you very much, Sama, for inviting me to deliver this lecture on this particular topic. Thank you very much. So,
Thank you. Yes, thank you, sir. Sir, if you can unshare the screen.
okay.
We will first have a photo session and then we will move on to the question answer session. So I would request everyone to please switch on their cameras so that we can have a picture. Dr. Swagata, Dr. Divya, Dr. Kaimu, Tyagi sir. Tyagi sir, you there? Okay, Ashwin, we can have one picture first, one or two. Okay, thank you. So let's move on to the question answer session, which will be moderated by Ms. Mrunal. Mrunal, please go ahead.
Thank you, ma'am. Thank you, Anand sir, for delivering such a wonderful presentation. Moving towards the question answer session. First question is from Savinudu Nudu Navaguma. He has two questions. His first question is the pressure gradient inside a tornado is from bottom to top? And his second question is the Coriolis force minimum at bottom of the tornado?
No, will you please repeat that question? First part is that from top to bottom, I followed that. So let me answer that first. So the pressure gradient force, what we are looking at is in the horizontal here, not in the vertical. So from the horizontal, of course, at the center it has to be a low. So the pressure gradient force will be acting that way from the outer part of the tornado to the inner part. And second question, I didn't get it. Will you please repeat that?
Yes, sir. His second question is the Coriolis force minimum at the bottom of a tornado?
Of course, the Coriolis force, irrespective of whether it is at the top or bottom, this is a very small scale system. So very small scale system. So the time scale involved is also very small when you talk about the tornado. So that way, the effect of Coriolis force is very small. So irrespective of whether, so I can't answer, I really don't know whether there is any difference between the top and bottom of the tornado, but in either case, the effect of Coriolis force is small in the case of a tornado.
Okay. So the next question is from Farnoosh. He is asking, do tropical cyclones like hurricanes include cyclostrophic flow?
No, because cyclone, again, it's a large scale system. So there we have to consider all the three forces. So there we will have to look at the balance between the pressure gradient force, Coriolis force, and the centrifugal force. So cyclostrophic flow applies basically to the very small scale systems like dust devils or tornadoes, maybe water spouts like that. Not for cyclones that.
Okay, so there are not much questions. The last question is from Vishal. He is asking, how do cyclonic and anti-cyclonic gradient winds influence weather patterns in different hemispheres?
Influence that anyway we'll have to look at how the cyclones and the depressions, low pressure systems, so many different ways it influence. But the purpose of today's lecture is not actually to look into those details. We cannot explain how for example, the cyclones develop, how it intensifies, how it decays. Those aspects we cannot discuss using this gradient wind approximation. So basically what I also mentioned that this only to look at the qualitatively, how the balance among different forces are happening. Only those aspects actually we can discuss with the help of this gradient wind, gradient flow. Not in which all ways these systems influence the weather. I'm sure that such details will be discussed in maybe in tropical weather lectures related to the tropical systems or synoptic meteorology lectures, I hope. Yeah.
Yes, thank you, sir. The question answer section. So I declare hereby the question answer session is over.
Thank you, Mrunal.
Thank you, sir. Thank you, Mrunal. Most of the candidates have rated it as excellent, so they want the PPT. I am sure Anand sir is going to
Yeah, I
share
will,
the
I will
PPT.
be
Yeah.
sharing that to you.
So definitely we will be emailing the PPT to all the participants.
Yeah.
Before we go to the Thanksgiving session, I would like to mention that till now around 203 participants have attended this session, and around 175 participants have rated it as excellent and very good. So it was a session which was full of first lecture which was full of lot of equations. And sir, you really explained it very well, because I think all the
No,
previous.
let me, I would like to say something. Actually, this particular topic I used to cover in 3 hours. So, so when you gave me 59 minutes, so I was not really sure how I will be able to explain all this. So I kind of cut short and went kind of real quick. So yeah, maybe because of that, yeah, maybe it's a little bit difficult to grasp everything what I discussed. So anyway, if anybody has any doubts, they can always contact me through email also, and I will be sharing the lecture slides. Yes.
Yes, definitely. Sir, once they have the lecture slides, probably
Yeah.
they will have questions, so they will be emailing you also directly.
Yeah.
And
Yeah.
if they email us, we will forward the questions to you.
Yeah, all are welcome to do that. Yes.
So, now I request Mr. Ashwin Jadhav from SPPU to please deliver vote of thanks.
Sure, madam. Thank you. So on behalf of organizing committee, I extend my sincere thanks to everyone who contributed to the success of this 6th lecture in our weekly online lecture series on atmospheric dynamics and application to climate sciences. We are especially grateful to Dr. Madan Lal Shrestha, who is Vice President of SAMA, also academician and a former DG, DHM of Nepal, for his welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Professor Dr. Anandakumar Karipot, who is visiting professor at SPPU, Pune, for delivering an enlightening lecture on natural coordinate system, cyclonic and anti-cyclonic gradient flow. I would also like to acknowledge Dr. Rohini Bhavar for moderating the session and Ms. Mrunal Naik for efficiently managing the question and answer segment. Additionally, I appreciate the guidance and support of all the panelists and EC members who ensured every detail was impeccably arranged. Special thanks to all the participants and attendees who join us from across the globe, and to the dedicated team members from Savitribai Phule University for their valuable role in organizing this lecture. Thank you so much.
Thank you, Ashwin. So I declare that the lecture series for today's lecture is over. The next lecture will be on 1st of March. And I think it will be delivered by Dr. Abhijit Sarkar, who is a scientist F, SAMA-WF, retired scientist F. His lecture will be on hydrostatic balance, geopotential, use of pressure as a vertical coordinate, a geostrophic, wind and horizontal acceleration. So please kindly attend that lecture. Tyagi sir, if any final closing remarks. Sir, you're muted.
No. Thanks to Dr. and all of you for having organized this lecture. And I think it's well received. So that's great. So, and you announced the next lecture schedule also. That's good.
I will